Oh my God, that thing's been beyond me this whole time. Enrolled students, 1, 2, 3, 4, and 2 online. Cool, we're at 33%. That's pretty good. I'll take it.
At least I was here 30 minutes early.
I only came early to see what was going on with this classroom. I haven't been over here. I actually took linear algebra in this class. But there sure as heck wasn't a bunch of TVs around the room at the time. That teacher is long dead. God, I've been here too long. All right. Welcome to the party. I'll give it a couple of more minutes. Might be a slow trickle of people coming in. Also, I just want to go to sleep. My 8-hour shift started 12 hours ago. I am tired. I bike to work, and it's 6 miles from my house.
Is that your e-bike out there?
Yep,
Nice.
yep. It's the cheapest one I could find that would get the job done. I get to the other side of town and back, and that sucker's dead.
Really? How much was it?
It's about 1,000.
Oh, that's not bad.
Yeah. Problem is, this phone here has about half the battery of that bike. I'm not kidding. Yeah, I'm not kidding.
Oh, wow.
My phone is 5,000 milliamp battery. That thing has a 10,000 milliamp battery, which also bugs me because they could just call it 10 amps.
Yeah.
You know, 1,000 milli, which is another lesson we will get at some point in the future. Okay, so if you missed it, we do have a sign-in sheet up front. I'm gonna have that here every time. I don't much care about the time in and the time out that's written on there, but yeah, just to record attendance. Those of you online, I do need your cameras on, so I know you're paying attention. I have watched a student fold an entire load of laundry before. And I don't know if you hear me. Oh, that's cool. Me too. I am also on meds that might make me fall asleep, but that's okay, right? Because that would mean class ends early. So, all right, well, cool. So we are a minute in to the first class, and I forgot how I was going to start this. I have a terrible memory. My name's Ben. I exist. I'm incredibly awkward, and I'm the nerdiest human being you're ever going to see in your life. If I lead with that, then, you know, the only way I can go is up. So for this class, you're going to see a lot of memes in the slideshow because, again, nerd. I'll tell you a little bit about myself. I'll tell you about the class expectations, the rough structure of the course. This sucker's going to be 6 weeks long, twice a week. I put reach out if you need help here because I'm going to drive that into your skull because honestly, a lot of you are going to have random questions throughout the class and you're going to be like, I don't want to be the guy that raises his hand and says something and you're all thinking it. Don't worry about it. Everybody's like, oh, thank God that guy asked because I didn't want to be the one. And class materials, of which there is almost nothing. So I'm Ben Wassum. It rhymes with awesome. Hello. Yes, that's a sign-in sheet. Cool. So I have an associate's in math. It is pretty much something that looks good on a resume and completely useless in the real world. People will say, what are you going to do with that? And they're like, I don't know, teaching a class with it. So pretty much just that. I've been tutoring since 2008. So I have a lot of math instruction under my belt. I'm very bad at the vocab of math. Sometimes I'll refer to the top part of a fraction as top thingy and the bottom as the bottom thingy. I don't much care what it's called. I care how to use it. And that's really what matters. Call me Ben. I hate Mister. It's not working for me. And I do care about you guys learning. So seriously, if something is confusing, terrifying, something bothering you, let me know. If you're feeling like you don't want to speak up about it in class, shoot me an email. Yeah, bug me. Bug me. If you don't want to say anything about it, throw an eraser at my head and get my attention. I'm cool with it. So expectations. So the Essential Education website that most of you already have a login for, that one's going to be where the homework is. It's all, it's kind of loosely considered homework. It's kind of a self-paced lesson sort of thing, kind of like if you've ever seen Khan Academy or any of those similar math websites. It's kind of like that. So you go on there, if you haven't been on there yet, it actually has you do a self-assessment. So you kind of run through like a quick little quiz. So set aside, 15, 20 minutes for your first login. But it quizzes you and then it's like, hey, you're bad at this. This is where we're starting. And then it just starts giving you lessons. The lessons are really short, only a couple of minutes long. When I'm having trouble putting together one of these slideshows, I'll usually go on it, slowly seek through the little bar at the bottom and be like, yeah, I'm stealing that. So it's actually very, very easy. And it also gives you kind of a glance at the type of questions that would be on the HiSET or the GED exams, because I'm going to give you the heads up. Most of those questions are going to be word problems and they're multiple choice usually. I think the HiSET is all multiple choice, and then the GED has like different options. Sometimes it's drag and drop. Sometimes it's like, I don't know, vague changes on the idea of multiple choice, but they're all kind of like that. So you'll see that type of problem on that website. So it is a very good resource. Use it. Another nice thing about Essential Education is that your hours in Excel are tracked. Everything kind of goes towards like a quota to get you up to the next levels and everything. The hours you spend on Essential Education do go directly to that. So that all counts. It counts just as much as being in class. So I mean, you could sit and do that for the next 30 hours and be like, cool, that's how long this class is. Literally. 12 classes, 5 hours. No? Oh no, yeah. 30 hours. This is a 30-hour class. That's it. Not too bad. Show up on time. We have a lot of ground to cover. In case you're not familiar with the general run of the HiSET test or the GED test, sometimes I'll just call it one or the other, because honestly, they cover the same thing and they give you the same thing at the end. So whoop-de-doo. It starts at number line and it ends at, I don't actually remember what it ends at. Unit test. Yes, I agree. Understanding statistical variability, which I'm like 50-50 on. So kind of a weird gap. Like I've said to a few of you before the class started, it's actually going to be done as 2 courses. There's this first 6-week one, then you kind of see how you're doing, then there's another 6-week one happening afterwards. I've kind of split up the lessons, and I'll give you the quick outline on that in a moment. So like I have there, communication. So send an email if you're going to miss class, if you're having issues. Like I said here, or said earlier, raise your hand, get my attention if you have questions, whatever. But yeah, just don't be afraid to bug me. I do have a day job, so it might not be, immediate, but, I'll try to get back to you as best as I can, help out, whatever. If you're doing the essential ed and you're confused, bug me. I don't care if it's some weird obscure math thing you saw on Facebook, bug me. People still use Facebook? It's Instagram, man. I don't know. I don't know. All these crazy kids and their things. I just say all of this. Blah, 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 blah. Yeah, so try to log into Essential Ed this week. You should have the username and password. If you don't, bug me or bug the Excel office because it's written down somewhere in your own handwriting, and you'll be like, oh, that's what that was. I don't remember that. Now, one thing about Essential Education that annoyed me when I first used it, you have to use the specific WNC login page. If you just go to essentialed.com and try to log in with the login you made, it just screams that you don't exist. So it took me a while to figure out you have to go directly to the WNC email or the WNC start page. I did send out an email a little while ago. You might have gotten, you might not have, with to all the email addresses that everyone registered to with the class. So that actually has a link to this. It also has a link to a Google Drive folder. So all of the slideshows that I make for this class and all of the notes that I take that I'm going to have on my notebook up here that you'll see on there in a minute. I scan all those and I upload them to the same folder. So all of my notes, all of my slides, all of it is going to be available anytime you need to. You can pull it up on your phone, whatever. Just trying to make it easy on you guys, because honestly, sometimes you're like, do I take notes or do I pay attention? Oh God, oh God. I'd prefer pay attention, but yeah, that's me. Another thing, Excel has social media. It's Excel WNC on all the usuals. And the main reason for that would just be if, like, there are class cancellations or something that everybody should know, they'll post it on there. To be fair, I haven't actually looked at it since the last class, so it's probably still there. Yeah, I probably should have double checked. I literally copy pasted most of this out of my last class. I'm not gonna lie. So class materials, something to write with and something to write on. That's pretty much it. I don't like math books. They're usually long and verbose, and if they're not long and verbose, they're like this thing where it's like, okay, page 1, you get a number line with fractions, percentages, and decimals all at once. And I'm like, why? This is literally clip notes for the first 18 years of your life. I don't like it. So yeah, I prefer, I'm just gonna go with explanations for my stuff, the Essential Ed website. That's all you're really gonna worry about. If you have a scientific calculator, bring it with you. That's going to come in handy on the later classes. If you don't, that's fine. I can pop over to the Excel room, borrow a bunch of them, bring them back here, and you can use them during the class. So that's perfectly fine. The main reason I have that on there is because the scientific calculator is generally what you will be either given or have like a little calculator box when you're doing the test with the HiSET or the GED. So you will have a calculator to use. So everything that you would normally do on paper that eventually you learn how to do on a calculator and never do on paper again, we're just gonna skip all that. Because, calculators exist and you're going to use them. Now, before I get into the actual math stuff, I'm going to give you a quick look at my big ol' ugly course outline. do not fear this. This is weird looking. I literally exported the scope and sequence report from Essential Ed and just kind of rearranged stuff and added stuff into it. But this class, I'm hoping to get through measurements, graphs and charts, and equations of lines. That's as far as we're going to really go into here. We're going to be playing a lot with like decimals, percentages, and you'll notice something weird about my outline here. People think I'm insane, but I think it's going to work out okay. And if it doesn't, please tell me. We're going to look at fractions, rates, and ratios, and then we're just going to jump straight into algebra before I even look at decimals and percentages. Because decimals and percentages, they work out okay, and the problems are a lot better to work with when I actually have a little bit of algebra to throw at it. So we're just going to be doing just basic linear equations and some inequalities. Yeah, I meant to have that one there. Okay. This is probably going to change throughout the class. Yeah, absolutely.
On the line on the parking part, no.
Cool. I have no idea what to do with that. Nobody has an ID. That looks like an ID. Is that an ID? Jose Rojas. Cool, don't know him. We're gonna figure that out. Somebody's gonna freak out somewhere. And I'm gonna take care of it eventually. Someday. All right. So yeah, we're gonna be doing decimals, percentages, exponents, roots, factors, multiples, equations, all that by about a month from now. So it'll be fun. It'll be fun. Oh, and as an aside, here is the stuff that's going to be the next class. So if you do stay and enroll in the next one past that, that's going to be like the harder stuff. There's going to be geometry. There's literally, when it says basic statistics, is about as basic as you can get. I've never taken statistics. This stuff's easy. So it's not bad. Don't ask me how I have a math degree without taking statistics. Quadratic equations is just when you go from x to having x squared. So that's not too bad. Systems of equations, I really want to fit into this class, but I'm probably not gonna. And functions, which is, honestly, I feel like I probably could have fit that into this class, but you know what? It's gonna be, we don't need it. Any questions while we're at it? Nah? Nah, all right, cool. Let's get into it. Let's get into really long math class. Everybody loves really long math class, right? Okay. So first of all, we're going to take a look at the real number system. Just getting into like the absolute basics. So the real number system is everything that isn't a real number. And you get up to like college algebra and you start playing with imaginary numbers, which is also pretty easy and is taught terribly by most of the educational system. But real number systems, not bad at all. You'll see natural numbers, whole numbers, integers, and rational numbers. So the rational numbers pretty much just covers most of it. You can actually see that they kind of start with natural numbers, and that's kind of counting numbers from 1. Whole numbers is counting numbers from 0. Integers adds negatives to it, and rational numbers are like things that can be a ratio. So fractions, most decimals, stuff like that. Now, this is hideous to look at, and it's hideous to wrap your head around, and I'm terrible at memorizing all of this stuff. So I went and found a nice little Venn diagram thing. Oh, and irrational numbers is down there at the back. It'll make more sense on Mr. Picture here. Pull the sucker up. Yeah. So you can kind of see that it all kind of fits nicely, kind of nested. Natural numbers are starting off with irregular counting numbers. Whole numbers just add 0, integers adds the negatives, and rational numbers is everything that's rational. So rational literally means it can be written as a ratio, which is a fancy word for fraction. So most decimals and all fractions work there. You'll notice that there's that little 3.56 with the bar over it. You'll remember that actually just means that the 5/6 repeats. So repeating decimals count as rational numbers. And then if they don't repeat, you got those weird little irrational numbers over there. Square root of 2, if I punch that into a calculator, that gives me something weird. 1.41421356237331, and it just goes on forever. So a number that doesn't repeat and it just keeps going on and on, that's an irrational number because it can't be fit nicely back into a fraction. That's why pi is hanging out there. Pi is 3.14 blah, 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 blah forever. And then any weird little square roots or anything that ends up just going on forever. If you punch it in a calculator and it goes on forever and it doesn't repeat, it's irrational. I'm pretty cheap about that. I absolutely throw everything into a calculator if I can and just double check. It works. It's a good way to go. So throughout the class, we'll just have some examples. Usually we'll kind of either write them out on my notepad here or just discuss them. So what I'm going to do is these ones are kind of funky. We're going to look at them and then go back to the Venn diagram because I totally don't expect any of you to have remembered all that by now. So we'll look at number 1. Number 1 is 15. Oh, that's the wrong way. There we go. 15. What's the first group that can actually click on? Natural, right? Because it's a counting number. It's above 0, so it counts as a natural number. Now, not just that, since it counts as a natural number, it's also a whole number, it's also an integer, and it's also a rational number. So anything that's this guy counts for everything above it. The only thing that's not going to hang out with is the irrational ones over here. So if I look at -20, well, the first one that starts using the negatives is integers, right? So it'll count as an integer, and it'll count as a rational number, and it won't count as any of the others, right? So it just kind of moves its way out, and it counts as everything outside of it. Not too bad, huh? And I will tell you, for the most part, we're just going to be referring to a lot of these numbers as integers. You use integers all the time. They're nice, they're neat, they're round, you throw them on there, they're numbers. It'll do. 0. Well, that would be whole numbers, right? That one's pretty easy. That one's kind of obvious. Because whole numbers, literally the only difference between whole numbers and natural numbers is whole numbers has a 0 on it. Cool, okay. Now you might say, hey Ben, why do we even bother separating these groups? I have no idea. I have no idea. I'm a terrible math teacher. Terrible. But this is something that does pop up and gets covered in all the high set materials I've seen, so we are totally covering it. Square root of 4. Any guesses?
Irrational?
Incorrect. I did that intentionally.
No, it's a really confident, but kind of.
Rational?
You said irrational?
Rational.
Rational? Well, it does count there. Now, yeah, I did that one on purpose because what is the square root of 4? 2. Okay, so it breaks down to a 2. So what does 2 count as? A natural number. Yeah, everything. So that one's intentionally a trick question. So you looked at the square root and you were like, yeah, it's going to be over there with all those other square roots. Not always. That's exactly why I am absolutely going to throw random trick questions on here all the time. Because that's how math works. You're kind of like, oh, here's all these easy ones. You're lured into a false sense of security. And then you get to the homework and you say, what the heck is that? I've never seen that. That's horrible. Why would you do that to me? So I'm not going to do that to anybody. I'm going to show you the weird ones. I'm going to show you the horrible ones. Don't ask me to make up problems because I absolutely will make up the most hideous problems you will ever see in your life. I do it all the time and torture people. It's great. But hey, the nice thing is you will never see anything that hard in your life. So number 5, 8/16. 8/16. I went the wrong way again. 8/16. Rational, yeah. Because even if you reduce 8/16, 8 goes into 8 once, 8 goes into 16 twice, so it's 1/2. 1/2 still just counts as a rational number. So no random trick questions here. 8/17. Any ideas? You are correct, sir. Everyone expected that to be a curveball, and it wasn't, because it was so close to the last one. Yes, I did that intentionally. I am a horrible person. But yes. So yeah, just a rational number because, hey, is that a fraction? Is that a fraction? Yes. So if they're fractions, then that's literally what the word ratio means. So if it's a fraction at all, it's going to count as a rational number. Well, that's probably a lie. If you look at that last like square root of 8/23 there, that can be written a couple of different ways. That, yeah, you can't fix that. That thing's ugly. Worst case scenario, punch it in the calculator, it gives you something weird, call it irrational. Cool. Do we have any questions on the real number system? I'm pretty sure that's all I had prepared for that. I have made no promises to this being a long class. Cool. More basic stuff. We've done a lot of basic stuff today. Yeah, I kind of get bored, but I mean, it's a 2.5-hour math class. You're gonna get bored. You think I feel I'm teaching? I don't want to be here. I want to be at home playing video games in the dark, being an absolutely useless human being, liking the idea of getting dinner and then just not moving. All right, so place value. Obviously, the decimal stuff to the right is going to come in handy really quick when we cover decimals, I think, next week. But for now, we're really only going to worry about the left side because we're looking at the whole numbers. How often does this come in handy? Well, give me about 3 weeks and it'll come in really handy. Scientific notation is a thing. You're all going to hate it. So we're a little familiar with it already. You got the ones place, the tens place, the hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billion. You know, you just kind of keep going. The one thing I always thought was weird about the decimal system is to the left, you have the ones. To the right, you have the tenths. Why don't I have a ones? That's not a good question at all. I just hate the terminology. I just kind of hate that it just doesn't mirror perfectly. I don't know. That's just kind of my deal. So decimal place values, you know, you would usually put the decimal and then anything to the right of the decimal, you start counting by tenths. So 100th is 1/10 of a tenth, et cetera, et cetera. And it's it's literally in the name and how it works. Decimal literally means deci. That's in tens. If you want to see something absolutely horrible, look up hexadecimal. I had to get familiar with that with computer science for a little bit, and it goes from 0 to 9 in one slot, and then you get A, and then B, C, D, E, F, and then you go to the next digit. Oh man, that's weird. That kind of hurt my brain. I didn't like it. But you know, it exists. Decimal's great. I like it. I don't want to mess with anything else ever again. So main reason I have that big ugly decimal infographic is rounding, because, well, everybody thinks they're pretty decent at rounding, and I like to break that and show you that you're probably not quite as good as you think you are. So we're gonna get that skill down real quick and then move on to, I don't remember what I put on the next slide because it's been 2 days and that is the limit of my memory capacity. So rounding, obviously, it's just kind of simplifying a number. You know, if you have like, you know, if you randomly had like, say, $15,456.23, you'd be like, yay, I got 15,000 bucks. Rounding, that's pretty much it. We're rounding 9,953 to the nearest thousand. 10,000 is a lot easier to deal with because, you know, you're 47 off. It's actually, you know, 953 away from rounding down. So rounding numbers, you decide which is the last digit that you're going to keep by its place value. You leave it the same if the next digit is less than 5, so you round down, or you'd increase it by 1 if the next digit is 5 or more, so you'd round up. So usually everybody's pretty happy with that idea, right? You're good at rounding. Let's see if we can break that. Let's see if we can make it a little bit worse, because rounding is really weird when you start playing with rounding to random spots in the decimal system and you got weird numbers. So I'm gonna real quick write these down. Kind of breaking my own concentration here. So we're going to round to the nearest 100. Everybody see that? It was so much easier in a classroom where I could turn off the lights and have a projector and not on a slanted table. All right, cool. About to make a joke about somebody getting extra credit for standing here and holding this down the whole time. But I mean, this class isn't graded, so you're good. It's just me telling you stuff. It's great. All right. So we're going to round 3250 to the nearest 100. Nearest 100, that's going to be this place, right? So nearest 100, are we going up or are we going down?
Either way.
I mean, I get the whole either way thing because it's right smack dab in the middle, right? So that's why I'm hearing different things. Right smack dab in the middle. But let's go back and look at Mr. Explanation here. So if the next digit is less than 5, you round down. If it's 5 or more, you round up. Now what's our answer?
3,200.
You would round up, because the next digit, you always, when you're rounding, you take that place value that you're looking at right there, the 2, and you look at the digit after. And you say, okay, is that 5 or more? Yeah, okay. If it's 5 or more, that sucker is going to round up. So we end up with 3,300 if we're rounding to the nearest 100. If you ask a bank, they're probably going to tell you to round down at all times, but you know, whatever. Money, that's a thing that I don't have. All right, the next one is, I don't remember, 323.5 to the nearest 10. Looking for the nearest 10. Ideas. She got 4 people. Nearest 10. 324 would be the ones place. But, well, that's the thing. That's why I'm kind of doing this intentionally. Yes, sir.
Wouldn't it just be wouldn't you round it down because it would be 3.5? So that's below 5, so.
See, this is why I have these problems here, because everybody thinks they're good at rounding, but I'm totally breaking your brains right now, aren't I? Isn't that fun? Oh my God. I'm gonna take whatever's in there, I'm gonna wipe it clean, and then we're gonna start over and put the good stuff in your brains. That's how it's gonna work. All right, so nearest 10. So all you gotta do, let's go back and where the heck? Okay, 2 slides back. Decimal place value chart. Well, where's the tens? The second digit on the left of the decimal point, right? Because, you know, we got, we are looking at this number in general. Let's look at the values. So the first one after the decimal point is tenths. Not tens, tenths. The TH there. Then we have ones, tens, hundreds, right? Okay, so here's the fun thing of this problem. What digit am I looking at? Which one's the 10 in the tens? The 2, right? Yeah. Okay, so do I care about the 0.5? No, I don't care about anything that's going on over here. This could very well be, let's make this weird. Let's, 2, 4, 5, 8, there's 7, 8, I don't know, 42. Let's throw all that in there. If I say round to the nearest tens, literally all I care about is that digit right there and the 1 after it. I don't care about anything going on over there. Not even a little bit. So if I'm rounding to the nearest 10, the next digit is what I'm looking at. The next digit, is it above or below 5? Below, right? Not 324, we're rounding to this digit right here. So if I'm rounding to that digit, 320. That's all we care about, because anything after that digit is going to be kind of rounded off. It's going to end up, you know, with a bunch of zeros on it. Hey, that's probably why they call it rounding. That's not me being like, you know, like sarcastic about it. That's like, that just literally just occurred to me. That's probably why it's called rounding. Because I round off everything else afterwards. It's all round, it's all zeros. Let's look at the next one. Where is the next one? Hi, next one, how you doing? All right. So I had 2 problems where I said round to the nearest 10 in a row. I don't remember why I did that. I don't know. Ben works in mysterious ways. So if we're rounding to the nearest 10, that's the digit we care about, right? The one in the tens place. What was that? Oh. Okay, so we're going to round to the nearest that. right? So, yeah, totally. Yeah, you'd look at the next one and be like, is that above 5? Yeah, it's totally above 5. Where would I round 499 to? Hello. Yes, totally. I have a sign-in sheet right here. You're welcome to pull up a seat wherever, but all the notes are going to be on that TV right there. So I recommend something where you can see it. Oh, my kingdom for a projector again. It's a cool TV. It's a really cool TV. It's better than my TV. I don't like it. You're going to come in here one day and I'm going to be watching a movie before you show up. I don't know what. It's going to be sci-fi or it's going to be fantasy. One or the other. All right, so we're rounding to the nearest 10. The 9 here, we look after it. We say, yep, there's a 9 after that guy. So that means we're going to round up. So if I round up 49, well, that guy has to go up, which means that guy has to go up. So this whole thing rounds up to 500. You just go up to the next integer, which is totally the only group from all of that real number system I covered earlier that I care about. It's the only word I tend to use out of that whole sheet on a regular basis. All right, let's look at another. I already forgot the problem. Okay, 0.74. 0.74. Another weird thing that I'm kind of a stickler for. You can't randomly just say 0.74. There technically has to be something out in front of that decimal to make it an actual number. So if you've ever had a math teacher be like, come on, you got to put the 0 there. That's why it's technically not a number until then. I'm absolutely that lazy guy that's going to totally drop that all the time, but you know, that's why. So if we're looking at the 10th place, that's going to be where the 7 is, right? So if I'm going to round to that nearest 10th, got a 7 here. We're going to look the digit right after it. Well, it's below 4, so you know that we can round down. So when it's rounding down as a decimal, you can kind of, I wanted to have a decimal on here just so you can kind of see how it works. But you kind of can kind of think about it as having that many digits, just so you can know that, hey, that guy is going to go down to be a 0. Because I know it gets a little murky when you start playing in the weird little, you know, pieces of a number territory. Yeah, that would be, that'd be rounded to the nearest thing that you'd actually care about. Like if I was playing with money and I had 74 cents, it'd be like, I'd rather just swap that out for a quarter or something. Convenience. But I do want to show that this is equivalent to 0.7. So even though there's no 0 at the end of this, with decimals, it's kind of funky. It's just saying, hey, I don't have anything right here. So you don't really need to necessarily have any trailing zeros in decimals, because this would be the same as like that, you know, it's the same thing. I don't need to say it. The only time you would ever really need to say it is if you have like a weird problem and it's like, you must have this many digits. And if you do, then cool, 3 digits, cool, there's 3 right there, 0.7000, lots of zeros. All right. Heck was I doing? Oh yeah, teaching math. Round to the nearest 100th. And I run out of room. Oh, what I just break? Projection control system. there a projector? I think there used to be a projector in here. Yeah, that would be where I'd hang a thing from. What'd I just break? Let's hit off, see what happens. It's what I'm playing with right now. I have no idea what's going on here. I also don't care, and I don't think it's doing anything, so maybe I'll just start pressing random buttons and see if I break the class. That could be fun. And yeah, let's just put it on top of this thing with buttons. That seems like a bad idea. I don't care. All right. What was I doing? Hundredths. That's what we were doing. Okay. So hundredths. Which number is in the place of a hundredths? Yeah, 4, right? Because you'd have tenths and hundredths. Yes? I keep hearing like bangs on the wall or something. I'm just gonna start, knocking back. Actually, when I was working at GameStop, I thought it was really fun. I just, we had a CPA in the next building over. And I just, went over, knock, 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 knock. And I waited for a minute and then I just hear pound, pound. And I'm like, yes, I like you. Thank you, random accountant dude, who was only there because your son owned the strip mall. Whatever. Okay, so we're rounding to the nearest that. If I'm rounding to the nearest that, I look at the digit after it, it's just a 1, right? Do I care about the 1? Nah, that sucker's gonna round off, right? This guy's gonna go round down. If I got 40 bucks, or 41 bucks, I'm gonna probably round off and say, yeah, I got like 40 bucks. I compare a lot of things to money because it's the one thing that everybody knows how to do and still says they're bad at math. Because I mean, when it comes down to it, you're gonna make sure you're getting paid right. Okay, and again, if it's kind of tricky for you with decimals, you can put that 0 there for now. You can, you don't have to, but you can. If decimals are funky, you can get away with that. This is my very lame attempt at a word problem that you can kind of ignore all of the words. If the bill at a furniture store comes to $3,257, what's the rounded value of the amount to the nearest 10? So we got 3257. Anybody want to throw a guess at me? Go for it.
The nearest 10 would be 5, so we would round up to 3250, or not 50, 60.
You are correct, sir. So you're looking at this digit, you look at the number afterwards, say, yup, that's above a 5. So you would round up. You got 3260. What did I do for the last one? I have a weird one. If the bill comes to 3284, what would be the rounded value of this amount to the nearest 10? I don't like that problem. Let's make up another problem. That's a boring problem. 7-ish. We're just gonna ish that. Let's say, let's just throw some random numbers at this. Let's say, I don't know, 6, 2, 5, 8 is literally how you could throw a math problem together. It's terrible. I don't know. Let's throw a 3 on there, and let's throw a decimal in there somewhere. Let's right in the middle, right in the middle. Let's say I wanted to round this to the nearest 1. Got 562.583. What would this guy be to the nearest 1?
563.
Yeah, 563. Because all you're looking at is that digit and the number after it. I don't care about what's going on over here. I don't care about what's going on over here. Let's say this is a dollar amount. What would this number be to the nearest hundredths? Like, you know, going and getting gas and everybody ignores that 9/10 at the end. But that 9/10 is gonna round right back up to another penny. Unless you do at least 10 gallons. So if you fill it up, you might save a penny. Yeah. So if you're rounding this to the nearest hundredth, that's gonna be this digit over here. So the 5/8. So the nearest hundredth would be this guy. Number after it is a 3. I don't care about the 3. 3 can go away. We're just gonna have 562.58. How we feeling? Everybody happy? Everybody happy to be in the 2.5-hour math class? Yeah, me too. Yeah, it's gonna be fun. It's gonna be fun. You only have to do this 12 times. Yeah. One thing that's kind of nice, I do like to do a little bit of review at the beginning of every class because honestly, you're totally gonna forget all this by Thursday. So I always do at least a little bit of review every class, so you are gonna see just about every concept twice. That way it kind of sticks a little better. I will say that one of the most useful skills I learned while tutoring was that if you want to like get this stuff down, go home later. You don't need to actually care about it too much, but at least read over your notes, get the gist of it, maybe do it tomorrow, just to kind of get it in your head. Otherwise, this is all just going to flush down the drain by the next class. I mean, there's 2 days till the next class, but there's going to be 5 days till the one after that. So it's all about retention. Oh. So everything we have after that point is just really fun stuff. Oh my God, why are there 2 monitors over there? Who uses that monitor? That's completely pointless. I keep losing the mouse cursor and it's over there and I push that thing off to the side because I don't care about it. So everything we have after this point is legitimately useful. These are things that a lot of times in, say, exams, the type of questions you would see on these types of things that they might show you an equation and they would ask you, hey, which of the properties is this demonstrating? That's one thing I've seen this used for in test taking. Otherwise, I honestly have a terrible time remembering which ones are commutative or associative or literally just those 2. So what I like to think about is just the root word. This one's a commutative property. What do you do when you're commuting? You're moving from one point to the other point, right? So it literally just says you can move numbers around and you get the same answer. So if I was adding 2 and 3, doesn't matter if you're adding 3 and 2 or 2 and 3, it's still going to end up 5, right? And the same thing works with multiplication. If I was doing 2 times 4 or 4 times 2, doesn't matter which way you look at it, you're still going to get 8. That's what's happening with the commutative properties. A plus B is equal to B plus A. You'll look at these properties, the letters are always just stand-ins for other numbers. If you're ever looking over this stuff or any other formula in any other class, and you're like, this is hurting my brain, whatever, you could swap out numbers in places of the A's and the B's and the X's and the X naughts, and you're gonna see weird stuff in algebra eventually, and it's gonna be fun. But yes, this is also a thing that I feel is not taught correctly because they teach it in this, usually it's multiple lessons, multiple lessons, and they teach you the addition ones, and they teach you the multiplication ones separately. And honestly, I mean, look at that, commutative property of addition, commutative property of multiplication. Doesn't that make more sense just teaching both of those things all at once? Look at that. That makes sense, right? I hate math books. I'm gonna write my own, and it's gonna have a really angry, sarcastic title. So yeah, that's pretty much all you're looking at there, is that you can move them around. Now, this does have a very useful application, one of which that I have been tagged in on memes on the internet very regularly lately, and I'm like, yeah, I tutored you. This is not a good sign. But with percentages, it actually works. That's actually comes in really handy. So you can look at the commutative property of multiplication. So say, okay, since A times B is B times A, that would also extend to things that have more than two numbers in them, right? 2 times 3 times 4 is the same as 4 times 3 times 2 is the same as 4 times 2 times 3. I don't care which direction it is, you're multiplying the same stuff together, it's going to end up with the same number, right? So it actually has a very useful application with percentages, because a percentage literally means out of 100%. So you can swap the percentage symbol with a 1 out of 100 fraction, and you would look at that as its own thing. You can kind of look at that percentage as its own thing and say, oh, okay, well, if I have some percentage of this other thing, you can actually move the percentage around. So for instance, as that example I have down there, what is 8% of 50? I would not be able to do that in my head. I don't care how good I am at math. No, I would just nope right out of that, right? But the percentages are reversible. If that percent symbol is the same as 1 out of 100, then it can attach to the other thing instead. 8% of 50 can be swapped around to 50% of 8. And that's easy. I like that one. That's, half of 8, that's 4. So that one's easy, and we like that. And yeah, I tried to do this in my head earlier when I was trying to compute how much overtime I had to shave off at work, and that was a mess, because I was like 0.85 of an hour, so let's move that around. Yeah, and then I was like, yeah, no, I'm not dealing with this right now, because I mean, it's first class tonight, so I was not playing that game. I've totally been that kid. Totally been that kid. Never had that teacher just be like, look at your paper and be like, yeah, you guys need to pay attention.
Can I see 2 seconds before, please?
Yeah, the thing before, that thing.
That.
Yeah, totally. Oh yeah, you weren't here at the beginning. Just so you know, I sent out an email with links, a link to the Google Drive that I put all of these slideshows in. This thing's actually already here on there. You could actually pull this up on your phone right now.
Thank you.
Yeah. Let's look at this. We got some fun problems. Yes, I know I said I'm doing, we got fractions later, and now I have fractions on this sheet, but these ones are easy. It'll be fun. Oops, what'd I break? Oops, what'd I break? Oops, I'm breaking everything. All right. Let's bring that back up. Cool. Let's figure out what 12% of 75 is. Can I kill the shadow? No? Okay, I'm not gonna care. So again, we can move that percentage around because I don't like thinking about this. This hurts my brain and makes me sad. So I'm gonna move it around. We're going to say we have 75% of 12. I like that better. I like that better, right? So 75%, that's 3/4, right? So what's 3/4 of 12? 9, right? So you just kind of separate it out that way, look at it in a different perspective. And now we know that 12% of 75 is 9. You're never going to use that specific piece of knowledge ever again in your life. But it's a useful application, right? Kind of makes some of these a lot nicer. Okay. So obviously I can just add left to right. If I have a calculator in front of me, I can mash it all in there. Yeah, you can get away with that. But the entire purpose of this is commutative property, right? So how can I make that make my life a little bit more useful, right? Well, I might look at this and say, hey, that 7 and that 3 go together real nicely, right? So I'm just going to move these around. Let's say I have the 7 and the 3, and then the 8 and the 12 together, because, you know, 8 and the 2 at the end, that comes in handy real nice too, right? Then I could just, you know, separate them out and say, okay, well, what's that? 7 and 3, 10, right? And then 8 and 12, 20. So we can jump straight to 30. Now, yeah, I could have added left to right and said 3 plus 8 is 11, plus 7 is 18, plus 12 is 30, and you get there. But, you know, depending on the type of problem, it might be easier to do it this way. I'm showing you the nice ones now. Later on in algebra, you might end up with some weird, obscure, hideous looking thing, and you'll spend all day trying to figure it out, and then somebody's going to walk over and just look at you and be like, those two could have gone together really easy, and you just slap yourself on the forehead. I've seen that happen. It's very messy. All right. Okay, yeah, that's kind of stable. I'm gonna roll with that. Okay, so this guy, you can kind of see what I'm gonna put together already, right? I mean, I kind of separated them out with signs because that was obvious. But the thing with the 14 and the 6, those are going to go together really nicely, right? So my first thought when I look at a problem like this is how can I approach this in a way that doesn't give me a headache? What can I put together first that doesn't suck? So I like this guy and this guy together right away, right? So I'm going to kind of reorder this so those guys are on the front. That also gives me a nice opportunity to say, hey, that 5, it's positive, so you can kind of have a plus there, right? So you can just bring that 5 in here and it's positive and you can kind of have that. there's multiple ways of writing these things. Wait until I start talking about how subtraction is the same as negative numbers. All right. So I'm going to put these two guys together. So we have negative 14 minus 6. What do we got?
Minus 20.
Yep. Then we got plus 5 plus 90. Those are nice to put together, right? Cool. Negative 20 plus 95. Who hates negative numbers? Yeah. 75. Yeah, because 95 and a negative 20, that's 95 minus 20. It's kind of useful, right? Comes in handy. I don't have to get a calculator for this ugly thing. I'm not going to be like, oh, this is a negative 9 plus 90 is 81, and then it's subtracting a 6. I mean, you can, but if I'm working some giant, horrible, hideous algebra thing with like 10 different terms on it, I want to do it in the easiest way possible. And heck, you're learning this stuff. Don't you want to do things in the easiest way possible? The whole goal here is avoiding effort. Something I live my life by. All right, the next one we have 1/2 times 1/3 times 20 times 30. Yay, multiplication. Love multiplication. Okay. So you can totally see where I'm going to go with this one, right? Because 1/2 times 1/3. I don't want to do that and then slap it on a 20. But if I reorder it and make sure that the 1/2 goes on the 20 and the 1/3 goes on the 30. And if anyone's unfamiliar, I like to do the dots instead of multiplication symbol because you do that in algebra. And well, in algebra, you really don't want everything looking like X's because you will get dizzy. So what's half of 20? What's 1/3 of 30? So what do I got? Yay! We're mathing. Aren't we having fun? You can see the soul strain from everyone's eyes very slowly. Don't worry, we'll get the harder stuff. Might say, hey Ben, why is it that in your slideshow you have the time symbol and on your notes you have a dot? And I would say, because I'm too lazy to figure out how to put the dot. Shut up, projector thing. I wish I could move. All right. Oh my God. Oh my God. Oh my God. I'm gonna smash this thing at some point. If I smash it, none of you remember who it was that smashed it. Is that fair? Good. Okay. Get away with that. Okay. So 2 times 3 times 10 times 4. I legitimately don't know what I was thinking with this problem. Who wants to multiply it in what direction?
Left to right.
Left to right? Well, that kind of undoes everything that I was doing. What else did we have? 2 and the 4? All right. I'm just going to reorder it that way. Let's do that bit. That looks good. I like that. Let's separate them out that way. 2 times 4, that one's an 8. 3 times 10, that's a 30. That works out nicely. I like it. I like it. I legitimately have no idea what I was thinking on this problem. I have a feeling there was another digit and I accidentally backspaced somewhere. It would have made more sense somehow. All right, 8 times 30. What do I got? How do we do that? 240, right? If anybody's thrown off on that idea, all you do is 8 times 3 and throw a 0 on it. It's significant amount of effort. I can do 80 times 30, no problem. It's just 8 times 3 with a couple of zeros on it. Multiplying by tens makes your life so much easier. Is all I prefer to do. Okay, I think that's all I have for commutative property. Don't worry, there's more properties. I know you're excited. Calm yourselves. Calm your- All right. So here we have the, breaking things. We have the associative properties. Same idea as the last one. There's one of addition, there's one of multiplication. And it's surprisingly similar. I get them confused sometimes. But it literally says that it doesn't matter how you group the numbers together if it's the same operations happening between them. So if you look at that first one, A plus B is in a parentheses, and then a plus C is on the outside of that. And that's equal to A being added to a B plus C. It's very similar to the commutative property. And in fact, we kind of use it in solving the last, ones. We're just deciding, what can group together. Basically saying it doesn't matter if you go left or right on these guys. So pretty much the same idea, just usually has some parentheses thrown on it. Where I'm gonna jump over to another page on my notes here. Here's the thing. You hate so much. I'm going to figure out where you're plugged in, and then I'm going to break that. Okay, so the first couple are literally just classroom sucks. All right. The first one is the first couple are literally just verify that the solutions are equal. So we're just going to do the left side and the right side separately, see that they're the same number, and be like, yay, we learned something. Okay, so in the parentheses, because you always do the parentheses first, you have 7 plus 3, that's going to be a 10. This thing turns into 2 plus 10, which is the 12. And over here in the parentheses, we have 2 plus 7. That's a 9 plus 3, which again adds up to 12. So they check out, they're the same thing. We're happy. We're oh so happy. Everything in our lives is finally coming together. It's 12 equals 12. You can kind of see we're still kind of doing roughly the same idea as commutative. It's just that we're not really moving things around. We're seeing that they end up being the same left to right because they're the same operators. So 5 and 8, 13 plus 2. That one's 15. And over here we have 5 plus 8 and 2 is 10. So again, we get a 15 and we're happy. Oh, so happy. Don't like no problems. I don't want the problems, let's get up. 16, change that to a 2. I don't actually know what I was thinking there. Yeah. Yeah, so this is actually something I might actually use that property. So I would get this problem, I would look at this and say, okay, well, yeah, I can put those two numbers together, but these two would work nicer together, right? And since it's just the same properties that are happening in between everything, we know that it's all going to add up to be the same thing because of the commutative property, right? So we know that this whole thing is equal to the exact same problem, just without a set of parentheses. So you could put a different set of parentheses on there if you wanted to. I don't care. I'm not going to. I'm just going to look at this and say, I would rather put those two together because that's going to make my life easier, right? Yeah, that turns into a 40. And then 40 plus 19, all we really got to do there is just add the 1 to the 4 and 9 to the 0. And we have a 59. So it's a little bit nicer than 19 plus 36 and then adding the 4. So you can actually see that you're dropping those parentheses. Now the next one that I just randomly threw together. It's similar. But looking at it, I might say, I know that this is the same thing. I know it's the same thing, but sometimes I do just like those pairings, right? Sometimes it works out nicer. They kind of fit together like really crappy Legos. So in a case like this, I would just work these guys. You're not going to go out of your way to fit the 16 with a different number or anything. You're going to do the easiest thing possible. So find the easiest way possible through a problem, run straight into it. Just go full stupid into the problem. It's great. So 42 and 58. Okay. 100 and a 16. Yeah, I wonder. I have $16 and I add 100 to that. I have $116. Good stuff. So do we have any questions on the properties so far? Any random insights of why are you torturing me with this stuff? Cool. Also, you can totally tell that whoever made this meme over here is British, because in Europe they call it maths instead of math. Because it's mathematics. What did we just do? We did a mathematic. When I do more of them, then it's mathematics. It's plural. Why is this a thing? I don't know. Do I want to know? Not really. So with the next slide, with the next property, this one ends up coming in insanely useful for algebra, to the point where I copied over my slide from the previous class. Then I was like, well, I don't want to do this until I cover this. Well, I don't want to talk about this until I talk about this. So I ended up making like a little mini lesson starting from this slide. So this is where things get like legitimately extremely useful. Like the other properties, they're incredibly useful, but you're gonna use them kind of unconsciously. You know to put things together in one way or another way. But with the distributive property, that's where you start getting into stuff that comes in really handy for algebra, for factoring, that sort of thing. It is okay. Hey, that means I have 3 online, 1, 2, 3. I got 9, 8 here. Oh my God, 12 out of 18. We went from 33% of the class to 66% of the class. Ooh. I want to see how many of you make it through the whole class. I'm excited. Are you excited? Nobody's excited. All right. Noted. All right, so distributive property. Guess what we're going to do with the distributive property? We're going to distribute. What a surprise. So it's a property of multiplication used in addition and subtraction. The property states that 2 or more terms in addition or subtraction with a number are equal to the addition or subtraction of the product of each of the terms with that number, which is very, I'm going to go with the word verbose. That is needlessly complicated to say out loud. It's just really useful to look at the bottom and say, hey, if I have a times b plus c in parentheses, this literally just means that that a can distribute into that parentheses and multiply onto both the b and the c, right? Pretty decent. Sometimes it's called the distributive law of multiplication and division. Let's not play with the division part of that for a while, huh? So I kind of worked up to this because distributive property is very useful, but it's also incredibly useful backwards. And it's kind of hard to explain that when you're going into factoring, that you're doing the distributive property backwards. So I felt like we would throw it on here right now. So you start seeing references to factors, and factor is just a number that can divide another number with no remainder. So it goes into the number perfectly. So like I have here, you can look at the number 12 and see how many times you can split it up as multiplications. 12, you can do 2 times 6, you can do 3 times 4. So you look at that and say, okay, everything that can multiply up to 12 is a factor of 12. 2, 3, 4, and 6 are all factors of 12. Now, what that's useful for is using the distributive property in the other direction. So if you look at the right side of the distributive property, that first line there, and you say, hey, we have the a times b and the a times c, you could say, hey, we have an a in common on both, right? So what you can essentially do is pull it out. You can factor that a out of both of those and turn it into the left side of that equation. So the a would come out of a parentheses, and you would have the b plus c in a parentheses. So I kind of have it written a couple of different ways near the bottom of this slide here. A times b plus a times c is equal to a times b plus c. Or chances are you'll more likely see it ab plus ac is equal to a times b plus c. Isn't that fun? Did I just make this weirder? Are we excited? All right. Are we dead inside? Are we dead inside? What time is it? Oh, okay, yeah. Yeah, well, I mean, I want it to be, but you know, I'm looking at this like, I gotta clock in by 6 in the morning. God, I hate mornings. Why do morning people exist? How do you wake up in the morning? I don't get it. I've been yawning since 4 this morning. I don't like it. Don't like it. This first problem is kind of half of the reason why I decided that I want to approach algebra a little earlier in some of these examples, because honestly, this is a really hard thing to explain without making the problem easier. Because normally you would look at this problem. I hate you, document camera. I hate you so much. I hate you so much. Oh my God. Normally you look at this thing and say, oh, I'm totally going to add the 3 and 4, right? Normally I would agree with you. That is 100% what I would do. But we are learning the distributive property. This is a problem that's actually easier to understand with algebra, but we're going to distribute that 2 in that. And all that's going to do is 2 times 3 is 6, right? And then 2 times 4, 8. And then you would add them together. So that's us using the distributive property. Does it look a little silly right now? Yes. Does it come in really handy in algebra? Oh God, yes. I don't actually know what I was thinking with this one. I wrote 6 times 204 by breaking it into smaller pieces, because that's a weird way to explain things. But I think I was thinking of the, they're teaching Common Core math and everybody's rallying against it and raging like, this is stupid, I hate it. And part of the reason is because I tutored half of those teachers that were explaining it, and they were confused by math too. So they don't know how to explain it either. But really, it's quite simple. A lot of times kids are being taught how to do things in their head, and you might not want to do a 3-digit multiplication in your head, right? So you would split it into smaller things. You would split it into 6 times 200 and then 6 times 4, right? Because I don't want to do weird, hideous problems in my head. But you split them up into smaller problems. 6 times 200, that's 1200. 6 times 4, that's 24. And then you could put them together, no problem, right? 1224. So, yeah, if you ever see a little kid and the parents are ranting and raging about how they're doing weird things with boxes with this type of thing, that's because the teacher's confused. But it works. It was literally the first time I've ever actually seen somebody write out how I do math in my head. And I was like, oh, this is useful, but it's god awful to write on a sheet of paper. Yeah. So we're going to solve this one by factoring out with the distributive property. So we have 16 times 6 plus 16 times 4. And you can totally just look at this and say, I'm going to punch 16 times 6 into my calculator, 16 times 4 into my calculator, and then add them together. Yeah, you could do that. But you might look at this and also say, hey, we have 16 and 16 in common, so we can pull that out. You would start a parentheses and say, okay, well, I just pulled a 16 out of this guy. So what do I got left? 6. Right? Then I pulled the 16 out of this one. Oh, we got that plus in the middle. Don't forget that. Pull the 16 out of this one. So what do we got? 4. So this is 16 times 6 plus 4. Yes, I have the worst handwriting on the planet. 16 times 10. I like that better. That is less hideous. It's a little more functional. It's a nicer problem. How do we feel? Are we happy with this? Confused? Is anybody confused? If anybody's ever confused, just, you know.
So what do you say that means?
Hmm?
What does that mean?
What does it mean?
Yeah.
It means that we are factoring a 16 out. So
Instead of the times you put it that with that, right?
yes, yes.
So that means the times.
Yeah, there's gonna be the ugliest thing and dumbest thing I ever write on paper, but this
That's
is,
what I got.
this is totally, that's that.
Ah, okay.
Yeah. That makes me uncomfortable to look at, but you know. If there's one thing that's fun, it's being uncomfortable. Okay, so now. Set up projector then. Yes, that's right. You're gonna have 6 weeks of me yelling at this projector screen thing. Likes to be. Okay. Exact same instructions. We have 26 times 3 minus 24 times 3. What's in common? 3. So we're gonna pull that out. We start a parentheses, say, okay, 3's coming out right here, so we have 26 left. Minus 24, right? 3's coming out there. All right. What's 26 minus 24? Oh, that's such a nicer problem, right? Whatever the heck is going on up here, apparently this and this are 6 apart. So I'd much rather do this. Ah, yes, I remember writing this and thinking, yep. I literally did this after I helped somebody with calculus and I realized that one of the formulas is just shorthand for this. If you did this big ugly string of things, you look at that and you would say, okay, well, I wonder what's in common.
7.
Yeah. So you pull it out. Here, we would have a 6 left, plus pulling a 7 out here. I'm gonna kind of like underline my little groupings here, just so it's, you know, we don't go cross-eyed. Okay, so I'm pulling the 7 out here, so I get a 2 plus 3 plus pulling the 7 out, we have a 5 plus a 4. And we can add these together in whatever direction we feel like. Now me, something commutative associative, blah, blah, blah. I would look at this and say, hey, that 6 and that 4 go together real nicely, right? Okay, so that's 10 plus, all right, so we have 2, 3, and 5. 2 and 3 is another 5, plus a 5, that's another 10. Yeah, so we have 7 times 20. So 7 times 2 is 14 with a 0 on the end because we multiplied by 20. So 6 times 7 plus 2 times 7 plus 3 times 7 plus 5 times 7 plus 4 times 7 is 140. Now, I would much rather do it this way than individually. And actually, that's actually a part of a big, horrible calculus thing where you're computing the area under a curve and you're making boxes for under the curve. And you end up estimating the area under a curve by adding the area of all these boxes. And it's like, well, all of these have the same freaking width. So why don't I just pull the width out and add up the heights? And that's literally how the formula works. So eventually this whole basic concept right here just gets thrown back at you in calculus where you're adding boxes together. And then you figure out what a limit is, and you figure out limit as the size of the boxes goes to infinity, or this little squiggly difference in the boxes goes to infinity. I don't know, it's weird. I'm not going to teach you that. You don't have to deal with that. Unless you want me to. You guys want me to teach you calculus? I got one nod. You gotta outvote that guy. Otherwise, you're gonna end up with calculus here. We're going full democracy in math class. Is that a terrible idea? That's a terrible idea, because I bet if I asked all of you when we should leave, you'll probably say now, right? Cool. Nah, you're all gonna be stuck with me for another, it's been an hour and a half, so 28 and a half hours over the next 6 weeks. Okay, so the next couple of slides don't really necessarily fit with this lesson, but I really wanted to cover these bases before we moved on to the uglier stuff. So they're just here, and they're useful, and they're weird looking, but this is something I realized did not get covered in any of the high set or GED stuff. And I'm like, this is the way you write the answers to all of these problems ever. So I don't know why it wasn't covered under that. But that is why it's here. So essentially, you know, everybody's kind of familiar with the number line, right? You got a number line, you draw a line on it somewhere, it's got endpoints or it goes on forever, and yay, it's a number line, right? So interval notation is effectively, it's a way of writing sets of numbers in the real number system. And I like to fit it in with the number line stuff because one, when you get to higher level math stuff, it's just really easy to get this down on a number line first before you start playing with it on a graph. And two, honestly, it's just really easy to deal with, because if you look at that, you know, I got that big ugly little thing under it in the curly braces there. We got the X, and then it has a bar. And that's actually how you would write this set of numbers in statistics. And it's kind of ugly, right? It's in some curly braces, and it says X such that -3 is less than or equal to X is less than or equal to Y. And that's weird. And we don't like it, right? So we're going to find a way around it. So interval notation is a nicer way of writing these. So with closed sets of numbers, you use brackets in interval notation. So For instance, that number line right there that I shamelessly stole from a random math website. You can see that it starts at -3 and it goes to 1, right? And both sides are included, right? They got a solid dot on them. You know, if it's got a solid dot, it's included. If it's got an open dot, it's not. So because of that, interval notation is literally just going left to right on a number line. It starts at -3, it ends at 1, and both sides are included. So you would write that with brackets on both sides, -3, comma, 1. And if you've ever done any graphing, you might say, hey, that kind of looks like a point on a graph. And unfortunately, this is one of those things that can get confused when you start looking at those. You just kind of have to be able to keep those concepts separate because you do run into parentheses with interval notation. So you also have the same sort of idea on open circles. Open circles get a parenthesis. It doesn't get horribly complicated past that. If it includes the endpoint, it's a bracket. If it doesn't include the endpoint, it's a parenthesis. And random thing that you're probably not going to need to know for this class, if it goes on forever, do you include the last number in forever? Nah, because that's going on forever, and I have no idea what the last number in forever is. So if you ever have to write infinity in one of these things, kind of like a sideways figure 8, it always uses a parentheses because you can't say it ends at infinity. So this is as ugly as it's going to get, and you're not going to do anything with this. So the top one is pretty common. You can have intervals that are half open and half closed. So the closed side gets a bracket on the -2. The open side gets a parentheses on the 4, right? So bracket -2, comma, 4. So every interval is kind of its own little set. You have a symbol, a number, comma, number, symbol, right? So this last thing is literally as ugly as you're ever going to see on any of these ever. And you're probably not going to do one of this. So if you have more than one set, you use that U guy. You got it's a fancy U, it's not the letter U, it's a fancy U, and it literally just means union. So it's the union of multiple intervals. So you're saying, hey, it's this piece and this piece and this piece. If you got a bunch of pieces, it's a bunch of pieces. So you look at that and say, okay, we got the left interval is -4 to -2. Both sides are included, so they both have a bracket on it. So you'd have bracket -4, comma, -2, bracket. Then you'd say, oh God, there's more of this. I don't want to deal with more of this, but you know it's going to keep going. So you just put a U on there and you say, okay, what's the next guy? So the next guy, and this is the weird part, this thing in the middle where it's -1 to 1 and has a hole and then 2, you have to treat that as 2 intervals. So -1 to 1 is its own interval. And you can see that happening on the second piece of the interval notation on the left here. It's parentheses, -1, comma, 1, ending in parentheses. And then it's going to have a union. So again, anytime you have another piece, you're just going to put that little U guy there. And then you say it's that 1 to 2 part. We ready to cry yet? No? Okay. Some people don't want it. All right. And then honestly, that last guy where it's just a dot, that's really fun to confuse people when they're in like trig. Because if you have to draw a dot in interval notation, everybody's like, what the hell do I do with this dot? Because it's not an interval, it's just a dot. So I put it in the little curly braces. That means it's the set of numbers and it's a 4. But you could also do like bracket 4, comma 4 bracket or some weird thing. Either way, you're not gonna have to do that. And if it's on any exam that you're ever going to see, then they just hate you. So before I get to the next slide of examples and stuff, let's look at some greater than, less than symbols, huh? A lot of you have probably seen these. Missing the or equal ones? Yes, I am. Yes, I am. All right, whatever. We'll be fine. So obviously an equal sign means so both sides are equal, right? We're pretty good there. You have the less than. That's when one value is smaller than another. And it's always when the left value is smaller than the right one. So you got the little part of it on the little side and the big part of it on the big side, kind of like that. I think there was something about, I don't know. Long ago, I heard a horrible way of remembering this with alligators, and I was like, I'm never going to repeat this, and I forgot it already. So I guess that's true. I did forget it. All right. And then the greater than symbol is just when the left side is bigger than the right side. You have the greater than symbol. The ones that are missing from this is the or equal to. So a less than or equal to is literally the same thing with a little bar under it. And that's saying, hey, it could be up to this point and it could be that point. Same thing with the greater. Gonna awkwardly stand here while people are writing things down. All right, so let's actually use this stuff. Boys, after they get their yearly compliment. Yeah. It's accurate, my case. I mean, come on, look at me. I figured out really early I had to be funny. All right, so we're gonna solve and graph on a number line, then write the answer in interval notation for all of this. Notice that I don't have any where there's more than one interval, because I'm not gonna make you do the union thing. I just wanted to show you guys just in case you ever run across it. So, hey, look, we're doing algebra. It's totally algebra. It's great. So, if you haven't solved these before, the whole idea is you kind of treat this guy like an equal sign up until the point where you might multiply or divide both sides by a negative number. Do I have an example for that? I sure do. That's not going to happen here. So all we're going to do, the idea here is we're going to try to get the x alone, and then whatever that ends up telling us, we're going to put it on a number line. Okay? So first thing we're going to do, we can look at that 9 plus 3 and we're like, oh yeah, those totally go together, right? So we throw those guys together. And then like anything else in algebra, if we have 3x is equal a thing, remember we're treating it like an equal sign at this point. You would cancel out whatever's on the x in order to figure out what x is, right? So this 3 is in our way from knowing what x is. So we're going to get rid of it. So it's multiplied by x right now. So if it's multiplied onto the x, we're going to do the opposite thing to it. So we're going to divide it off. We're gonna divide that by both sides. 3 divided by 3, how many times does 3 go into 3? Once. So we just have an x here. Yes, we could technically put a 1x, but you never really need to say 1x. If I'm walking around with an apple and somebody has to look at me and be pretentious and say, that is 1 apple. Yes, but it's an apple, and I don't care to go out of my way to say I have 1 of it when I have 1 of it. And then 12 divided by 3. Oh. We have x less than 4. We're going to number line that guy. This is going to be the lazy application of a number line. This is how I do all of my number lines. Oh my God, I'm so. Usually I'll go out of my way to kind of put a little bit around it, but yeah, totally. That's all we really need to worry about, right? And we are saying that x is less than 4, so it doesn't include 4. But it's everything less than that. So if it doesn't include it, we would use an open circle. And it's everything less than that. You remember that thing I said about infinity and said that you're not going to have to worry about it for a while? Guess what? We're worrying about it on number 1. Isn't that great? Now, interval notation is pretty easy on this guy. Because what happens all the way to the left? Well, it goes on forever, right? So here's the thing with infinity. Okay, one of those eyes goes over here. We're just going to roll with it. My brain doesn't always work the best. Them neurons is misfiring a little bit. So infinity is this guy. Now, the annoying thing, the truly annoying thing, is that in math, well, I mean, it makes sense, but if you're going down forever, that's a different level of infinity than going up forever, right? Like if your bank account's going down forever, then that sucks. If your bank account's going up forever, awesome, cool, let's waste all of that. I'm going to buy out all the cable companies, shut them down, and just flip off their CEOs. So the idea here is you end up also having the problem of infinity existing and a negative infinity existing. That is very, very useful for interval notation. And then later on, graphing things, and yeah, it just has a bunch of applications. If it goes down forever, it's negative infinity. If it goes up forever, it's positive infinity. So what's this guy doing? It's going down forever, right? So on our left, we have negative infinity. Now, again, do I include the last number in infinity? I don't know what the last number is in infinity is. So that one always gets a parentheses with interval notation. Always. That looks terrible, but whatever. So interval notation, you put whatever symbol you need, the first bit, comma, and then where's the interval end? Well, it ends at 4, right? Does it include 4? No, didn't include 4. We got an open circle, so you use a parenthesis. That's all interval notation is. It's literally just looking at a number line and translating it into numbers. It's not bad. Interval notation is always left to right. Always works out this way. There is, and it's short to right, and I don't have to, you know, I literally, you don't ever want to deal with this. I mean, yeah, you could kind of be done, but also, no, I don't want to do that. It took me too long to figure out how to do these little curly braces on paper. I had to do these a lot. This was stupid. I don't like it. So I like interval notation. It's great. If you ever take a statistics class, you'll have to probably deal with that. Okay. Next one, we have 2y is less than -8. Same sort of idea. We're going to solve for the variable. Might say, hey Ben, why is this one a y and the last one is x? And I might say, because it doesn't actually matter. Because it's a letter and I felt like it. That's all. It's a thing I don't know. What thing is it I don't know? Could be a -5, could be a -6, could be a -1,000. It's whatever makes this true. So again, we would have, honestly, almost the same number line. Except in this case, we would have a -4 instead of a +4. That just kind of keeps going in that direction, -3, -2, -1, 0, etc. And it works out about the same. Open circle here because it's not included. Goes on forever to the left. So we end up with about the same answer, right? Goes on forever to the left, so it's -infinity, comma, goes up to the -4, doesn't include the 4, so we use a parenthesis. Was it intentional that I ended up with almost the same answer? Totally not. And number 3, we have 12 is greater than or equal to x plus 5. So again, we do what we got to do to get the x alone. We just subtract the 5 from both sides. We end up with 12 minus 5, 7 over here is greater than or equal to x. Now, if I go to my number line, I go to my 7, and it's greater than or equal to, so it's a solid dot, it could include it, right? Which direction am I going? Left or right? Everybody check out? I know I am. Right? So here's the thing about this. Here's the thing about this. You want it to be to the right because of the symbol, right? Because it's greater than. When you see greater than, you think, okay, it goes to the right. But if our symbol, if our variable or unknown is on the right, inequalities are kind of hard to read that way, right? Because if I have to mentally think of 7 is greater than or equal to x, that's really strange to think about, right? It's easier to think of, say, y is less than -4 because you're thinking, okay, everything less than -4. Yeah, so exactly. So what I like to do on problems like these, just so I don't, end up looking at it funky or looking at it and thinking, okay, it's going one way when it's not. Whenever I'm doing inequalities, I personally like to have the variable on the left because it's easier to read that way. It's going to make your life easier if you just flip this whole thing around. Now, if I flip the whole thing around, it changes the direction of the sign. So if I flip this guy around and I say x is less than or equal to 7, oh, okay, then it's going to the left, right? It's a lot easier to read if the variable is on the left. So whenever you're doing inequalities, anything like that, I like to make sure the variable is on the left. If it's not an inequality, if you've just got an equation and you have an equal sign, then, you know, 2 equals x is the same as x equals 2. It doesn't matter. But how you read it does matter when it comes to inequalities. Make sense? Everybody good? Everybody kind of good? I'll say kind of. What kind of? All right. This one, I have negative y is less than or equal to 2 plus 3. Okay. Same sort of thing. The 2 and 3 we can put together real easy. Got a 5, but we have a negative. We don't want the negative. We want our variable to be positive. We're going to divide by a -1, right? You can either multiply both sides by -1 or divide by -1. It doesn't really matter. It's the same thing. I prefer to look at it as dividing everything by a -1 because if I have a bunch of things, then it helps me just kind of like put that underneath everything rather than trying to write off to the side. So I usually just divide. So this guy becomes positive, this guy becomes negative. And anytime you divide or multiply both sides by a negative number in inequalities, that direction of the sign does have to flip. So instead of a less than, we now have a greater than or equal to. Yeah, I totally forgot the interval notation on that last one. It looks like this. There we go. That's for the notes. It looks like that. It ends at the 7. We're happy about that. That problem totally existed just because I wanted to go over that. This problem completely existed because I totally wanted to go over that. Same sort of thing. We have the -5. We have everything greater than or equal to it. So it's closed circle, goes off forever that way. And as an interval notation, on the left side of our interval, we have a -5. It's included, so we use a bracket. Comma, on the right side, it goes on forever to a positive. So it's a positive infinity. We never include the last number infinity, so we have a parenthesis. Everybody happy with that? All seems thrilled. All right. Me too.
I have a little bit confused in five is positive, right? 5 divides, yes, here. 5 is positive, so if we divide between -1, it will be,
It becomes a negative. Because anytime you have, sign wise, I mean, if I have a positive times a positive, we know that's positive, right? If I have a negative times a positive, well, it just kind of negates it, right? -1 times a 2 is going to be a -2, right? That's not what I was trying to write down. Had an eraser? I lost the eraser. So, and then you would have a negative times a negative being another option. And negative times a negative, the negatives cancel out, so you end up having a positive, right? Well, the same sort of thing happens with fractions. Positive divided by a positive always stays positive. Negative divided by a positive ends up being negative, and a negative divided by a negative, that's fun to write, always ends up being a positive. So it ends up working out that way. So essentially, if you have a positive divided by a negative, well, that we only have one negative here, so that kind of makes the whole thing negative. It's actually a useful thing to know, but if you have something like this is equal to something like this, which is equal to something like this. If you have one negative hanging out on something, it can kind of move around. You can get away with that. That's actually really useful, and I use it all the time. And it can be incredibly cheap. I have totally skipped like 15 steps on high level like calculus things by being like, hey man, you can just flip that around. Makes life easier. Does that make a little more sense? Yeah. I'll leave that there for a second. Excellent. That kind of works. That kind of works. I can totally get away with that. Totally works. All right. Okay, so I got another 26 minutes of your lives. Let's see what I can fill them with. What was I doing? Oh yeah, fractions. Who loves fractions? Who hates fractions? Okay. That's why I wanted this to be a day one thing. I was literally at work and the other day and taught somebody fractions in 5 minutes on the back of a piece of copy paper. It's not as bad as you think. Because let me take a wild guess. You get a problem in your homework and it would have fractions in it, and you'd be like, that's that point I'm gonna miss. I'm just gonna skip it. Or you write what you think it's going to be, and then you try to purge it from your mind and you never look at it, right? Because it's fractions and you're scared of fractions. But the nice thing is that they're really not hard. You just kind of have to sit down and decide, okay, I'm going to get this down because I hate this and I don't want to hate it anymore. Because, I mean, everybody hates fractions. So let's have fun with that. So that's too far. Okay, cool. All right, so there's 3 terms that you'll see for fractions. Proper fractions, mixed fractions, and improper fractions. Proper fractions are the nice ones, 1/2, 1/3, 2/3, 6/8. I don't really care. Just where the top one's smaller than the bottom one, and you can look at that and say, yeah, that kind of makes sense, right? That's a fraction, that works. Mixed fractions are literally just a combination of an integer and a proper fraction. So it's not really its own type of fraction. It's just kind of a term you get used to. So that's just, 1 1/2, 2 1/5, stuff like that. Then you get improper fractions. Those are the ones that are funky to look at. I call them top heavy, 15/4, 3/2. Now the nice thing is that, I kind of have it written down here. Proper fractions and mixed fractions are easier to visualize, right? You can think of 1 1/2. 3/2 is a little weird. 15/4 is a lot weird, right? So in terms of when I would use one versus another, if somebody asks you how far something away is, let's say a couple of miles into town. Let's say, I don't really care. Let's say Arby's. Somebody decides they hate themselves and they're going to go to Arby's. So let's say, okay, yeah, it's just, you go down the road, about 15 thirds of the third miles. You go 15 thirds miles in that direction and you'll find it. You want to slap the guy, right? Nobody wants to hear that. That's a stupid answer, right? You know, you would reduce it. You would say, okay, it's like 3 miles, 5 miles. It's 2.5 miles down the road. Nobody wants to hear 5/2 of a mile. So when it comes to proper fractions and mixed fractions, if you're asked, say, you know, if you're in like, you know, GED test, high set test, and you know, you're working out one of these problems and you're like, do I have to leave this as a improper fraction? Can I move it to a mixed fraction? Ask yourself the question and say, if somebody told me this, would they want to slap me? That's pretty much it. Word problems are usually where you're going to answer with proper fractions and mixed fractions. With regular equations, algebra stuff, improper fractions are the way to go. They're a lot easier to work with. In fact, anytime you see a math book that teaches you how to do math with mixed fractions, it literally says turn it into an improper fraction, do the math, and then turn it back. And yeah, so I hate mixed fractions with a passion. I hate working with them. They're stupid and I don't like it. Improper fractions are much easier to work. But again, they sound stupid. So we're going to jump into fractions with all of our fun operations. And funny enough, I think addition and subtraction of fractions is harder than multiplication and division. Because addition and subtraction, you have to have the same denominator, right? You know, I got a couple of pies and I'm putting the pies together after like a family Thanksgiving that used to happen when my family was happy and wonderful. Back in the day, tell you one thing, when you see your grandma's house driven into with a SWAT van through the front window on the news, whoo, that's a story. I couldn't find the video when I went looking for it a few years ago. All right. So yeah, say you're putting pies together and you got half a pie and you got a third of a pie and you're putting them in the same pie pan and somebody's like, how much pie is there? You would say, I'm not going to tell you, it's a lot of pie and I'm not going to think about this. It's a lot easier to put together if they have the same, they're kind of the same phrasing. I don't like adding a half and a third, but I might like adding, you know, 3/6 and 2/6, because then they're in the same frame. You frame them to be roughly the same idea, and then you can put them together nicely. So when it comes to adding and subtracting, you always have to have a common denominator. So the bottom has to be the same. Those are a couple of the terms you'll have. You'll have numerator and denominator. Numerator is the top thing, denominator is the bottom thing. So common denominator literally just means make the bottoms the same. So then you got multiplication and division. Who likes dividing fractions by fractions? Is that just a fun idea? No, right? But if I asked you, how many times does 50 cents go into $2? What would you say? How many times does 50 cents go into $2? Anybody? 4, right? Well, how did you get to that? You think, okay, 50 cents twice is $1, twice is $2, right? So you literally just divided $2 by $0.50 in your head, but you don't want to think about it that way, right? You do it as multiplication. Well, that's literally how you do division with fractions. You don't want to do division with fractions. It hurts your brain. So you actually just turn it into multiplication by doing some funky stuff. You actually flip the second one upside down, multiply instead of dividing, and congratulations, you can divide fractions by fractions. That's it. It's not too bad. Now, with multiplication, which again, is gonna be the same thing with division. You just multiply straight across. You don't have to have a common denominator. We don't care about a common denominator. You just multiply the tops together and multiply the bottoms together. We got fractions. Hey, look, it's how I feel every day. Bunch of fractions. What time is it? 12 after, nope, 13 after. Do you think we could pull off 9 problems in 17 minutes? Yeah, screw it, let's do this. Let's do this. Most of the problem is going to be writing them down. Better write them all down real fast. Cool. We've got a bunch of fractions. Everyone loves fractions. Wait till we do algebra, and I'm going to throw a ton of fractions in there. And I'm going to throw tons of fractions into everything that I can in this class. You're going to get fractions down. And it's not going to be a problem. Now, the first one I set up real nicely for us because it already has a common denominator. When we're adding and subtracting, we just get a common denominator and go across. So yeah, 14 minus 12. And it's always over the same denominator. Now you can reduce. If you get down to it and you're like, hey, 2/6. Yeah, you would say, okay, well, 2 fits into both of these. And you can reduce by that. 2 goes into there once. 2 goes into the 6 3 times. So usually, if you're doing these types of problems, you do want to reduce the answer. Look at number 2, 6/7 minus 2/14. We could go 2 different ways. Because, I just, stress common denominators. You might think, okay, I need to get this one up to 14, right? Well, I'm also really cheap about this because I set this guy up to be reducible. So sometimes on these types of problems, you will get lucky and you'll be able to see, hey, I could reduce those right now. And that will actually get me my common denominator. That does happen sometimes. I've actually seen some really complicated looking problems that people go through all kinds of weird, funky stuff. And I'm like, that would have reduced at the very beginning and that would have made your life easier. And then heads go into boards and disappointment everywhere. It's great. So 6/7 minus 1/7 is 5/7. 6 minus 1 is 5, and that's all the math you really have to do there. Negative 5/3 plus 2/3. I know you're saying words, but I can't hear any of them. Yeah. Yeah, negative 3/3, which is -1. Because 3 goes into 3 and cancels out, we get a -1. Now, if you're a little thrown off by that, you could very well just cancel out threes and say it's -1 divided by 1 and anything over 1 in itself. So you end up with there anyway, but you can kind of jump into that. So, number 4. That kind of works. Number 4, we have 7/3 plus 5/7. That one's not as easy, right? Yeah, 21 would be our denominator. The idea is you find the first thing that both of these denominators can multiply out to. Now, I don't want to say it's always going to be multiplying both of the numbers together. That is a common denominator. It's not always the lowest common denominator. So if you rely on that in a pinch, then you might have to reduce at the end. But if you're okay with that, embrace reducing. Now, as it is, you would just look for the first number that both of these have in common with their multiples. 3 and 7 both go into 21. So you would have to get the denominators to 21. So what you're going to end up doing, this one you would multiply by 7/7 to get that denominator. And this one you would multiply by 3/3. Now we've seen it 1,000 times, but do you know why we're multiplying by 7/7 and 3/3? Why can I not multiply this by 1/3? So the idea is, what's 3/3? 1. 1 times anything is the same number, right? So what you're doing whenever you do this is you're multiplying by a funky looking 1. So anything times 1 is itself, you're not changing what it is, so you're safe. So you just, on each of these, you multiply across. 7 times 7 is 49 over 21 plus 5 times 3, 15 over 21. Add them together. That's 64 over 21. And that won't reduce because 64 is a whole lot of 2's. 2 doesn't go into 21. Cool. Number 5, we have 3/4 plus 4/3. Guess what our common denominator is? 12, right? We're going to multiply it by 3/3 here, 4/4 here. So we end up with 9/12 plus 16/12. 9 plus 16, 25/12. That's why I actually say adding and subtracting is harder than multiplying and dividing, because on each of these, we already did multiplication twice, right? So when we get down to here and we're finally looking at the multiplication problems, these ones are really easy. So for number 6, we have 2/3 times 4/5. Go straight across. So we end up with 8/15. Then we have 6/5 times 2/5. Go straight across. 6 times 2, 12. 5 times 5, 25. Not bad. Now down here, we have reached division. And remember, we have divided $2 by 50 cents by not dividing and multiplying instead, because dividing by fractions sucks. So instead of doing this, we leave the top one alone and flip the bottom one upside down and change it to multiplication. By doing that, you end up with the exact same thing, just so much easier. 3 times 3 is 9, 4 times 2 is 8, Question?
So does it matter which one you flip?
Yes, you always have to flip the bottom one.
From the bottom?
Yeah. Yeah, it does break if you flip the top one. And then number 9, we have 2/9 divided by 3/5. So you can change that to 2/9 times 5/3. 10 over 9 times 3 is 27. So we did 9 problems in, what was that, 10 minutes? Ain't bad. Ain't bad at all. Are we slightly less terrified of fractions? At least a little bit. I'll take a little bit. I'd take that inch. If I can get that inch, I'm happy. Okay, so what was I gonna torture you guys with next? Because we're gonna call it good. I'm just kind of curious. Because I just kind of kept going and I got like 13 more slides on here and I'm like, God, what was I? Oh, okay, that would probably be useful. Yeah, that'd probably be useful. Oh yeah, these would all be useful. Yeah, this is all useful. How about we do that next time? Does that sound good? Start with fractions next time, but weirder fractions. It's gonna be great. We excited by this idea? None of you are excited. Okay, cool. All right, so I don't know how many people here are used to the idea of a college course, but yeah, you're all free. You're good. Go home, get some sleep, eat some junk food, hate your lives. I gotta clock in at 6 in the morning. I'm gonna cry. I have to poke people in the arms with a needle. Oh my God. It's very anxiety building when you're phlebotomy, I gotta say.
Can I copy the answer from book? Last,
Oh yeah, totally. You're still writing, yeah. 100%. Just be like, Ben, shut up. Just put that over. Yeah, I'm cool with it. Do any of you have questions or anything? No? You can totally go. Yes, you are free. Yes, I'm talking to you online. You are free to go. Oh, yeah, you're good. You're all good. Everybody's happy. If you forgot to sign in, please sign in. Otherwise, I'm totally not going to know your name and can't write it down. Totally going to do that every single time because honestly, I'm really lazy. Now I got to figure out how to return a wallet to somebody. Yeah. See everybody Thursday. What games do you play? What games do I play? All of them. However, I am currently playing Xenoblade Chronicles 2 because 3 came out and I never finished any of the others.
Oh, we don't have to sign out? Oh, no.
No, I don't care. The sign out's really useful for me if somebody like leaves early, but yeah, otherwise I'm just gonna assume everybody's here till 8:30, even if I break early.
See you, thank you.
we do Thursday, right?
See you later, Thursday. Oh, yeah.
Rising storm.
Irma. I've always wanted to try Irma, and then I'm like, oh my God, I'm gonna die.
The controls are a little bit much. Every button on the keyboard. Yeah, you can't read. It's hard to read because every button does something. So you have to switch.